Okay, guess we'll get started today. So I'm going to continue with the probability today. And last lecture I kind of ran through the first 8 or 9 pages of the chapter, and mostly because it was material that you should be pretty familiar with already. I'm going to slow down a little bit, and today I'll cover these topics: random variables, probability mass function, probability density function, the CDF, how to generate random variables from a particular distribution, expectation and variance. So each topic is sort of small and self-contained. The reason I'm going through them in some detail is because having a very good understanding of the meaning of random variables and these expectation and variance and these other things is important for understanding information theory, which we'll start with on Monday. As I've mentioned in Piazza, I will not be covering moment generating functions in class, or the only distribution I'm going to look at from the set of standard distributions is the Gaussian, because we'll be using the Gaussian in information theory. And then I'll cover just section 1.5.2, this is Gaussian, and then I'll cover in some more detail Bayesian, Bayes theorem, and joint probability distributions and conditional probability distributions. And so all these will become clear next lecture, because understanding joint is actually super important for understanding information theory, which is all about conditional and joint distributions. Okay, so I'm going to start with random variables, and I'll give you a sort of a more intuitive understanding of what a random variable is. This clock is okay. So we often have the situation where we have a variable. So think of a variable in the sense of in computer science we have some kind of variable, and it assumes certain values. So if I say int x, it's an integer, and it has some values, basically 0 and is 2 to the power 32 minus 1 if it's a 32-bit integer. So it takes a certain set of values, okay, and you can say that this set of values that it assumes is you can call it this range 0 to 2 to 32 minus 1. We'll call that the domain D of this integer x, and so that's the domain. Okay, so let's say that the value x it has is, let's say, 24. Then we can think of sort of two things really. One is the the variable x itself. I'm now going to use a slightly different notation. Capital X to me denotes the variable, and small x is actually represents this number over here. It sort of says this is the value it took. So we have this notation of x equals x. It seems kind of bizarre, but what we're saying is that this is the variable, okay, in the computer science sense of the word variable, and it takes on a value, and we don't really care what value it is, and we're going to call that small x. Now, I did not invent this notation. I don't like it. I find it very confusing, but that's what every textbook uses, and if you want to study probability, unfortunately, you're stuck with this notation. So as long as you remember that the capital letter denotes the variable in sort of the computer science sense of the word, and small letter denotes sort of the value assumed by it, things will be okay. And I'll go over the notation a little bit more because there's a little bit more confusing notation. Okay, but having said that, so in really what I mean is that x is what it should be calling over here as int x, and then whatever value it takes is x. And normally we would use like a or b or c or something like that to represent constants, but it's not a constant, right? It's a variable, so we use small x. Okay, to come back to this now, let's say that we have some reason to believe that this value x, this integer x, takes on only 3 values. Okay, it actually takes on the values 2, 7, and 9, and it has some probability associated with taking on those values. Let's say it's 0.2 and 0.7 and 0.1 are the 3 values it can take of 2, 7, and 9. So in some sense, the domain is restricted. It's only these 3 sets. So we'll write the domain D equals 2, 7, and 9. And associated with this domain are certain probabilities, okay, which are these probabilities. I'll show you the notation in just a moment. But the point I want to talk about here is that we have some variable whose value we don't know exactly. So if somebody comes to you and says, what's the value of x? You say, well, I don't know, but I can tell you that some probability it's 2, it's some probability it's 7, some probability it's 9, and that's all the different values it can take. If with probability 0 it's 1, it's probability 0 of being 2,500 or whatever, right? So what's going on is that we know something about it, but not everything about it, okay? And what we know about it is that the probability of it assuming certain values, okay? Now, let's go back to the last lecture where we talked about sample spaces and events and outcomes. And we're saying, okay, I have something over here which takes on these values, but what's the sample space? What are the events? What are the outcomes? What's going on over here? And what we try to do is, in the mathematical sort of formalism, is that we associate the values assumed by the random variable x with an underlying sample space. Okay, so we have some sample space S, which corresponds to what? It's a set of outcomes, right? So we have outcome O1, O2, okay, and we may have actually infinite, so I can't really say On. It's some set of outcomes over there. Okay, and the important thing is these outcomes are distinct. So we know which one it is, and they're mutually exclusive by definition. So we have this set of outcomes, and what we do is that with this sample space, we can group them into sets. Okay, we can say O1 and O2, and then maybe O3 is its own little thing over here. And this set, this subset, is what we call an event. So now I need the colors. So we call this subset an event. So if I were to kind of draw a circle on these two, this is event. Okay, and then obviously we can associate a probability with this event, which is because your probabilities associate outcomes. I kind of said I skipped over that part, but we know that there's some probability of outcome O1 equals some value. Let's say it's something in this range of 0 is less than or equal to this probability less than or equal to 1. So corresponding to each outcome, we have a probability. And from the axioms of probability, because they're in a mutually exclusive, distinct, and they're independent, these outcomes, so we say that these events, the probability of this event is the sum of these. So we have a way to compute the probability associated with the event. Now this is the event probability. If I say event equals E1, then I can talk about the probability of E1. And now what we're going to say is that when we take the domain D, this event probability corresponds to the probability that x equals, let's say, x1. Okay? So each value assumed by x can be thought of as being corresponding to an underlying sample space, okay, which may be implicit. In fact, the sample space may be identical to the domain, right? In many cases, the value, the outcomes may just be 2, 7, and 9. So the domain D is 2, 7, 9. The sample space is 2, 7, 9. Life is good. We don't have any problems. We just say here are 3 outcomes, the 3 events. Events are singletons in this case, and the outcomes of whatever process is going on are 2, 7, and 9, and the probabilities are associated in this way. But in some cases it's not. We saw last time that we had this occupancy, buffer occupancy, which is low, medium, and high. But low, medium, and high are not outcomes per se. The outcomes are the buffer values. The values are 1, 0 to 10. So we have 11 outcomes, 0 through 10. Those are the O1 to O10, or O0 to O10 in this case. And we have these events. The events are groupings of outcomes. And corresponding to groupings of outcomes, we have a domain which has actually 3 values, low, medium, and high, right? So low is not an outcome. There's no experiment that says my outcome is low. The outcome is some distinct value in the range 0 to 10, but the domain is low, medium, high in this case. So x1 would be sort of low, medium, high, etc. So the point I'm trying to make over here is that we start, when we talk about, when you talk about, here we start with the variable, but actually underneath is a sample space, and you need to be very careful to know what that sample space is, okay? Because if you make mistakes in the sample space, then you're basically going to have trouble figuring out what's going on, okay? So we have a mapping essentially from events in the sample space to the domain, and that's what gives the probability structure to the random variable. So random variable is random because the value assumed by the random variable is drawn from the underlying sample, okay? Either this is blindingly obvious or it's very confusing. I don't know which one it is. But I can tell you, speaking for myself, that it sounds very obvious, and then when you start using it, it's very confusing. You say, oh, where did that come from? So at this point, it looks like I'm just talking about the same thing for a long time. It's because it turns out to be not that straightforward once you started trying to apply it in a real context. Okay. So any questions about this? Okay. Okay, so by and large, when we talk about random variables, we kind of ignore the sample space and we ignore the events and the outcomes and all that. Unless you're trying to prove theorems about it, that's something we don't really talk about. We just say, here's a random variable, or we say a stochastic variable or something like that, and we just assume that you know what the underlying sample space is, and that for most purposes, it's good enough. I'll make one comment here, which is that you will notice that in our discussion of control theory, we have actually ignored all randomness. So we have some input and we have some output. And the output is related to the input by differential equation, and the differential equation is expressed in a number of different ways, the transform, etc. But we never allow the possibility in our discussion so far that an input will lead to a random output, okay? And actually, that's a problem with classical control theory. It's not stochastic, okay? So there's a very large discipline called stochastic control which says, okay, I pressed hard on the accelerator, but there's some probability that the car accelerates. Maybe in some cases it doesn't. Maybe it has some stochastic output. So what we can say then is that there is some input, and the output is not one value, but it has a distribution. We'll talk about a distribution just in a minute. Or we can say the output is a random variable which assumes values from some range, okay? From some domain, actually. And but we don't actually discuss that in control theory, or we didn't discuss that in control theory. Just as a footnote. Okay, any questions here? All right, so now we can pick up a little bit of pace, because this actually is, I wanted to get this through, because we'll refer to in information theory as messages as random variables, and that gets a bit confusing unless you have this clear in your head. Okay, so we have two kinds of random variables, discrete and continuous. And in a discrete random variable, we can enumerate the domain, okay? And there's a simple way to enumerate it, there's 1, 2, 3, 4, etc. In the continuous one, and by the way, I'm going to talk only about real variables. So when I say low, medium, high, those are not real values. Those are literals, right? But in this discussion from now on, we're going to assume that they're all real variables. And if they're real variables, then we can say that we can just enumerate the set of real values. If it's continuous, then the domain is a subset of the real line. Okay, and again, for simplicity, we'll assume it's one subset rather than a set of subsets. We can generalize this to a set of subsets, but we won't. We'll just look at a single subset of the real line. Okay, and so that's discrete and continuous. It should be intuitively clear what it is. So any time interval, for example, is continuous. Whereas if you look at the buffer occupancy, it's discrete because you have set of discrete values. Okay, the next concept, which is quite important, is that of a distribution or a mass function. So in many cases, we don't really care what the value assumed by the random variable is, because actually we don't even know what it is. You know, if somebody says, what's the value of x? Well, it's 1 of 2, 7, and 9. Okay, that's not giving you too much information. But if I could tell you this, this probability over here, it has some probability of being 2, some probability being 7, some probability being 9. I can speak of this probabilities as having some structure, and in fact that's called the probability mass function, and that's used for discrete. And all it means is that it's basically saying for each value that the random variable can assume, what is the probability of that particular value. So here is where I'm going to, and then in the distribution we have a slightly different meaning. I'm going to come to that in just a minute, but let me first tell you what the notation is. So I'm going to actually, because without the notation things gets very complicated. So notation, so x or capitals is a random variable. Small x is going to be the value it assumes. I already said this. Capital P stands for, of E is the probability of an event. Okay, so capital P always means the probability associated with some event in the underlying sample space. On the other hand, small p, okay, means probability also, but this is a probability associated with that x takes on some value, let's say x equals x1. So the probability that the random variable x takes on the value x1 is called small p of x equals x1. Okay, and what this really means is that there's some underlying event that corresponds to this called E1, and this capital P of E1, but that's kind of hidden. But we want to remind you that we're talking in the domain space rather than the sample space, so we use small p of x equals x1, and this is often abbreviated as small p of x1, for example. So small p of x1 means that's a probability that the random variable takes on the x1, and just to make life interesting, when we talk about the distribution or the probability mass function, we use the notation p of capital X. This is a probability mass function for a discrete random variable x. Okay, and just to keep things clear, I call it xd is a discrete, and for continuous pxc, it will be the distribution, which I haven't defined yet. So you got to be very careful. Small p of capital X is, or capital XD is the mass function, whereas large P of capital X doesn't exist. Large P of capital X doesn't mean anything. Small p of small x means the value of the probability that the random variable capital X assumes the value small x. Okay, that's the meaning of that. Yeah.
As of now, it says like there is a one-to-one mapping from the event space to
right.
the domain of D, right?
That's domain D of the random variable X, right?
Yeah. So there is a one-to-one mapping.
Yes.
So on what basis is that mapping done?
Up to you. I mean, it's up to you to say that what is the event corresponding to a random variable taking on a particular value. It's in the problem definition.
Okay, so in that case, are we assigning? You told it should be discrete. That means it should be enumerable, right?
The set of events would be enumerable in this case, yeah.
So in what scenarios we have enumerable events?
Well, if you look at if you look at buffer contents, right, I can tell you that the buffer value is something, whatever it is.
In
right?
that case, it is directly the sample space.
It can be directly samples, but I can say that if the buffer value is between 2 and 5, then it constitutes one event. I don't really care, right? I have so I'm sorry, it is one event with multiple outcomes. Correct. Yeah, there's going to be a one-to-one mapping from the event space to the domain space in this case. Yeah.
So if you say that it's between two values,
right.
Again, that doesn't really convey a particular numerical value.
Well, okay, so we have, in the buffer case, we have a bunch of outcomes, right? Each outcome has some associated individual probability coming from the process, from the understanding of the process. We sum up those probabilities to find the probability of the event, and then there's a mapping from there to the value assumed by the random variable. Right? But the value assumed by the random variable could be from a different space, for example, low, medium, high, whereas the sample space has outcomes which are 1, 2, 3. So they're different spaces, right? 1, 2, 3 is not the same as low, medium, high. But the events over here correspond to those, correspond through some mapping into the domain, which is low, medium, high. Right? So that's why you have to be careful that the domain is not the sample space. Okay?
I thought that I was wondering why, how can you enumerate an event?
How can you enumerate an event? No, you can enumerate the set of events. Okay. You can say that, well, you can certainly enumerate the domain because it's discrete. So the random variable assumes values, let's say, 2, 7, and 9. And then I can say the value 2 corresponds to an event this, okay, which corresponds to a set of outcomes, which is some set of outcomes. The event, the value 7 corresponds to some other event.
My first question, is there any way in which you are assigning value 2 corresponds to this set of events?
No, it's up to you. It's up to you. As long as you say this is how I do it, it's up to you. You don't have to. I mean, it's not. It's how you model the problem, right? It's a modeling issue. Yeah. Okay, it gets more confusing once you go to continuous. That's why I'm trying to hold off on continuous for a bit. Okay, but is this notation clear? The capital X, small x, and so on. Okay, let me just talk about continuous, and then I'll take a break. So, for the discrete case, we have this domain. For the continuous case, so I guess in the discrete case, the distribution is pretty, actually the probability mass function is pretty clear. In the continuous case, we actually have the following situation. So we have basically we're going to define the density function, and density function is also called the distribution. It's the same thing. Okay, or distribution of x, the random variable x. Okay, and let's say, and we call that the density function is called f of x. It's a standard notation, f of capital X, and the meaning is not that the let me show this over here. So let's say on the x-axis I show the subset of the real line. So this is the line over which I have some values, and then on the y-axis I show f of x. So basically it's 0 here and it's 0 here. In this I have something like that. And what this f of x says is that if I take a small value around x1, if I take a small region around some value x1, then the probability that the random variable assumes a value in the range around x1, okay, so the probability, let me be precise over here because, I didn't actually, so it's going to be a probability of an event, actually no, it's going to be small p that x1 minus delta by 2 is less than equal to the variable x less than equal to x1 plus delta by 2 is going to be equal to f of x1 delta, okay, for in the limit as delta tends to 0. Okay, so what we are intuitively saying is that if I take a really, really small region around x1, the area under the curve in that region, in that vicinity, which is this little rectangle over here, is the probability that the random variable assumes a value around that little thing over here, around that value x1. Okay, the reason why we have to do this is because the probability that the random variable takes on the value x1 at x1 is basically 0. Okay, so if I have a random variable, it's a continuous random variable defined, let's say from 0, 1, and I say what's the probability it takes on the value 0.5? 0. Okay, what's the probability it takes on value 0.6? It's also 0. So we have this kind of funny situation where the probability of any individual point is 0, but the sum of all these 0 value probabilities is what? It's 1. Okay, So we have a paradox, right? We take a whole bunch of zeros, and if you make them all together, it becomes a 1. So it's like the euro currency, right? Each country individually is a 0, and you take them all together and they become, a strong currency. So this is financial engineering for you in a nutshell. So it's like a probability density function. So let me take a minute more to describe the density function. So the probability of some event in the sample space happening is 1. Okay, that's again axiom of probability. So probability of sample space S itself is going to be 1. Now, something happened. Okay, otherwise the sample space is not going to be universal, right? It's not going to be exhaustive, and we assume it's exhaustive, which means that in the case of the density function, integral minus infinity to infinity, because it's a part of this real line, it's got to be the case that fx dx is equal to 1. So that's always going to be the case. And this is another way of stating this. This is a limit would be to say that the probability that probability that x1 is less than equal to x is less than equal to x2 is going to be given by integral x1 to x2 fx dx. Okay, so a common mistake is to assume that the fx value is the probability of the value at x, and that's not the case. Okay, and I'll show you an example of this. So let's say that we have a uniform distribution. So actually, so we have uniform distribution. So fx is equal to some constant is the uniform distribution. Okay, and let's say that it's defined over the range 0.5 to 2.5. Okay, then what we have is that integral 0.5 to 2.5, let's say c dx is equal to 1. Okay, and this of course means that 2c equals 1, so c equals 0.5. So okay, if I were to draw it, what it says is that this is 0.5, this is 2.5, it's 0 everywhere, and here to here it's 0.5. Okay, so that is exactly what I was trying to say over here. We have something over here, some random function. In this case, it just appears to, it just is basically a step. Okay, and it doesn't mean that the probability at of x equals 1 equals 0.5. Okay, that's one common mistake that you make. It's not. Okay, whereas in a discrete function, what we would have is that we would have some set of discrete values like so. And then if this is 0.5, then you could say, yeah, sure, maybe these two 0.25, 0.5. You say, yeah, the probability that the value of 1 is assumed is 0.5. So you can read off the probabilities from a probability mass function, but you can't do that from a density function. From a density function, you must work with the integral instead. Okay. All right, so this brings me to the homework problem, because again, I was trying to drive that point home with that. So the first one was so fx there was cx square, and is defined in the range 0, 1. So we know that integral 0 to 1 cx square dx equals 1, which implies that cx cubed by 3 0, 1 equals 1, which implies c equals 3. Okay, so that's the answer. It's about as simple as that. And so again, it doesn't mean the probability of some value in the range is 3. I mean, it doesn't make any sense, right? You can't have probability of 3. So that's why we get, okay, but that's the answer over here. Okay, any questions about this?
So what does that c equal to 3 intuitively mean?
That means that fx equals 3x squared. Intuitively, what this means is that the probability that it lies in some tiny range delta, okay, around around this value, let's say x1, is going to be 3x1 square. Okay, that's the probability delta. So the probability, if I will go back over here, the probability that it rises in the range x1 minus delta by 2 less than x is less than this is going to be fx delta, or is going to be 3x1 square delta. Okay, and so that's what it is. So if you think about it, x1 squared is going to be is less than x is less than well, in range 0 to 1, right? So we're going to have something that looks basically like this. Okay, this is going to be 1, this is 0, and goes, and this is 0 here, and it's 3 times that. Okay, and so the closer you are to the 1, the higher the probability. Okay. And any questions here? So it's not uniform; it's increasing. So values towards 1 are more probable than values closer to 0. But at the value of probability at any single point, of course, is 0. Okay, any questions here? All right, so let me now go into the cumulative CDF density function, or the cumulative distribution function, CDF. So CDF is just the sum. Okay, so CDF. So let's do it for the discrete case. In the discrete case, the CDF is defined to be capital F of any value x is given by sigma I such that x sub I is less than or equal to x. Okay, probability of the value x sub I. Okay. So, which is equal to, or which is also the same as probability that the variable x is less than equal to x. So, we use this as the shorthand for x less than equal to x. Now it should be clear that what we're really talking about is the random variable x is less than some chosen value small x in its domain, and we're looking at the sum, and it's less than or equal to. So if you had a distribution function like this, it was let's say this is 0.2. We have the same thing over here, 0.7 and 0.1. Then fx would be, in this case, so this is this is fx. Then capital F of x is going to be, well, 0.2 over here, because less than equal to this is going to be 0.2, and then it goes up to 0.9 over here, and then it's going to be 1.0. So as you can see, it's going to be monotone increasing. Yeah?
What does it say underneath the cell again?
Over here?
Sum.
Oh, I such that xi less than equal to x. I'm sorry, I should. You want to make it? I can. This is what I wrote. I such that x sub I is less than or equal to x. Okay, that's zoomed in for you. Okay. Sorry, yeah, it's okay. So is this clear? I mean, this should be pretty straightforward. You guys have seen it. Okay, let me do the continuous, and then we'll do some stupid pet tricks with distributions. If you've seen David Letterman's show from a long time ago, he had this thing called stupid pet tricks, cats on Roombas and things like that. So we're going to do stupid pet trick with distributions. So continuous. In the continuous case, the continuous case, the distribution f of x, the cumulative is given by integral minus infinity to x, and we'll just use a different variable to avoid confusion, fy dy. Okay, and this is basically also denoted as probability that x is less than equal to x. Okay, so the x over here is not the integral over here, but it's this guy over here. Okay, in many textbooks, just to make life fun, they actually use integral minus infinity to x fx dx. Okay, where you're supposed to know that this dx is just a temporary variable, and that's the x we really care about. Okay.